Hello there. Welcome to Virtual Flylab. It's actually called Flylab JS on this website. It used to be called Virtual Flylab. All right, so why are we at Virtual Flylab? And the reason is because we're doing a linkage and mapping assignment. And so I've emailed everybody all kinds of information about this. But these are the documents. So here's the instructions. And these instructions go into a lot of the background and theory about linkage and mapping. And then you're going to be assigned a set of mutants, and then you're going to map them relative to each other. And then you're going to include all your answers on this sheet. That's a Google Sheet. You're going to make a copy of it and then fill it out and share it with me. And you're not going to download it and make a PDF version of it or Word or anything. You're just going to share the link with me. And then I wanted to show you these mutants. So each of you was sent a number. And so these are the numbers. And these are the mutants. So these letters correspond to the mutant abbreviation. So let's say set 1 has AP. If you look over here, AP means apterous. Apterous means no wings. B is black for black body. You look over here, black body color. So this just kind of helps you find where the mutant is in that Virtual Flylab program, because it has different categories like wings and body color and eye color, that sort of thing. So you get 9 mutants. That sounds like a lot, but these 3, the last 3 in each case, are all X-linked. And so those, you already know what chromosome they're on. You know they're linked to each other because they're X-linked, and you just have to map them relative to each other. Then these other 3 or 6 are on autosomes, and an autosome is a chromosome that's not an X chromosome. And some of these are linked to each other and some aren't. And so your job is to cross them together in certain ways to figure out if they're linked. And then once you figure out a bunch are linked, so if you have 3 of them that are linked together, then you can calculate a genetic map based on those 3. If they're not linked, you're done. You don't have to do anything with those, because if they're not linked, they're not linked. So the first part is to cross them together and ask which ones are linked to each other. And if you have a group of genes that are linked to each other, that is creatively called a linkage group. And so you have a couple of linkage groups, and then within each linkage group, you want to calculate the distances and come up with a map between those. So all of these documents describe all that. And then, but where do we get the data? How do we do the crosses? That's what I want to talk about today. And so this Virtual Flylab thing, or Flylab JS or whatever, everything I'm going to talk about right now is all spelled out in this document here. So I think it's easy. If you like videos better, watch this and do this. If not, do that. I'm going to try to say the same stuff, but I probably won't say it word for word, but who knows. All right, so I'm going to show you how to do it. So you have 2 genes, and you want to map them relative to each other. And now I kind of interchangeably use the word gene and mutant and locus, so I should probably explain that a little bit. So a mutation is a mutation in a gene. And then you can tell the difference between the mutant gene and the wild type gene. And so you can make a fly heterozygous, and then you could do a cross, and you can look at how many are wild type and how many are mutant. So you need to have a mutation to track how the gene is inherited. It's because you need to be able to see the differences so you can see what's going on. And so anyway, so the mutants that we're going to map are, and so I should start this over. Let's see. I'm just going to start that over altogether. So I'm going to close out of that and start it back up again. So to get into this site, it's Flylab JS, and then the link is on the assignment. All right, so we're going to start out. And so this is a female fly. I can tell because it says female here. And just kind of partly because of the quirks of the way this program works, we're going to start with a female that's all wild type for everything. So that's the first step. Pick a wild type fly. And then we're going to put the mutants that we're interested in mating and in mapping into the male. So we're going to design the fly, and the thing that we're doing is eye shape. We're going to map the eyeless gene. And the first one we're going to try is body color, and we're going to make that ebony. And just to give you a spoiler alert, the first thing I'm going to do is to show you what it looks like when it's not linked. So over here on the right, we have a fly. It's a male. It's eyeless, and it's ebony. It has a dark body. So we make those guys together. Then we have these offspring, and the offspring are all wild type, but they're all heterozygous. Now these genes are not X-linked, so we know that these are all heterozygous for both genes. Now, here's a big mistake you might start out with, and that is crossing these two together. But if you cross those two together, that's going to be a dihybrid cross. We don't want to do a dihybrid cross. What we want to do is a test cross. We want to have one of our flies be a dihybrid, heterozygous for two genes, and do a test cross. So on this page, we know that, and the dihybrid has to be a female. And that's just because in flies, for whatever reason, there's no crossing over in males. So the point of a mapping cross is to make something heterozygous, and then see if you get crossing over in between those two genes. So you have to put it in a female so that you allow crossing over to happen. And then we have to do a test cross. So she's heterozygous for both genes. This guy back up here on the right, the original male parent, he's homozygous recessive for those two genes. So we have to use that because it's a test cross. A test cross, you always have to use somebody who's homozygous recessive for all the genes. So then we made them together. And we get some results. And here's our cross. Female heterozygous for both genes, male homozygous for both genes. Here's all the numbers of the different types of flies we got. But we don't want to look at all these things and add them up. We want to use a table. So we're going to go to Analyze, get a table. These genes aren't sex-linked, so we won't have any difference between males and females. So we ignore sex. And what do we got? We got 240, 254, 256, 254. That looks to me like a 1-to-1-to-1-to-1 ratio. It's not exactly a 1-to-1-to-1-to-1 ratio because it never comes out exact. But you would probably agree that that's close enough. But that's not good enough for us to just eyeball it and say it's close enough. We're going to do a test of the hypothesis. So we can actually do chi-square with this program. And it does the calculations for us, which is kind of nice because then we can kind of focus on the logic that goes along with the chi-square test rather than worrying about doing all the calculations. So if we expect, this is what we observed. And so always when we do this kind of a thing, we're testing our hypothesis for whether or not it's showing independent assortment. So if it's showing independent assortment and we do a test cross for two genes, then we expect a 1-to-1-to-1-to-1 ratio. So that's like saying 1/4, 1/4, 1/4, 1/4. Then we have to calculate the expected values. And the way you figure out expected values is you take this 1/4 and you multiply it by the total. So we counted basically 1,000 here. So if you were to expect 1-to-1-to-1-to-1 and you count 1,000, you expect 250, 250, 250, and 250. But they'll do that math for you. You don't even have to do it. So you test your hypothesis. Here's the probability that we expect, 0.25 for each category. We multiply that probability times the total that we observed, because that number is going to change. If we counted 10,000, we'd expect more. And then we do the chi-square equation, and we end up with 0.65, and that's our chi-square value. But that's not the p-value. So what happens is, I think when you're first doing this, you take that value and you think it's the p-value. But that's not the p-value. That's the chi-square value, and we use the chi-square value to figure out the p-value. That's a really low chi-square value, by the way. We have 3 degrees of freedom because we have 4 categories. And degrees of freedom is always n, which is the number of categories, minus 1. So we have 3. If we go to a chi-square table, we'll come up with a p-value. that p-value will look like this. In this case, and they call it level of significance. So here it's 0.88. 0.88 is way higher than 0.05. 0.05 is always a cutoff. If we say 0.05 or greater, we accept our hypothesis. What hypothesis are we accepting? We're accepting the hypothesis that it's a 1 to 1 to 1 to 1 ratio. That's actually kind of more of a prediction than a hypothesis. But what underlies this is independent assortment. So because we accept this, we say, yes, independent assortment is occurring. Well, if independent assortment is occurring, then they're not linked. So we just say these aren't linked. They're not in the same linkage group. We put them into two different groups, and we move on. So that's it. You can, if you want to. I've never really done this, but you can add this to your lab notes in this program. What I would do, you probably can't see it, but on my screen at the bottom, I have this little scissor thing, this snipping tool. So just do some kind of screenshot and cut out these results, copy them, take them to whatever document you're working on, and paste it in. And whenever you do that, you might write a little thing about that. So you're going to have to save these results from all your different crosses. So that's how I would do it. Okay. So we did that cross. They weren't linked. So let's do another cross. And so we're gonna test it for something that I happen to know is linked. And actually, the mutants I'm picking happen to be on chromosome 4 of fruit flies, and I just happen to know they're linked. So now we're gonna do shaven. Did we do shaven last time? No, last time we did eyeless, right? So we're gonna do eye shape, which is eyeless, and then we're gonna do bristles, which is shaven. All right, I did this cross wrong already because I'm doing this in the female. We don't want to put this, so that's going to be so here, let's do it that way. So we put it in the female, we select it for mating, and then we design the male, we make him all wild type. So I'm doing it wrong. You can do it this way if you want, but you have to do an extra step. So now I've got my female is homozygous mutant, my male is homozygous wild type. If I cross them, they're going to be heterozygous for both genes. And so now I've got a female that's heterozygous for both genes. That's good. That's what I need. But now I need a male that's homozygous recessive for both genes. And I don't have one on this page, so I have to make one. If I do the cross the other way, I didn't have to make it. But I can make one. I don't care. Select this female. And I guess I have to design another one. So I selected her. Now I'm going to go design another one. And I'm going to take shaven, eyeless, male. So this will be a test cross. So now I've got my female that from before that was heterozygous for both genes, and I just made a male that's homozygous recessive. So that's another way to do it. Make your flies. These are your results. You don't want to look at that and count them all up. You want to analyze it this way. The sex of the flies just makes it more complicated, so we ignore that, and we get a result like this. So this is the result. This is how every single cross is going to look. If the genes are linked, you're going to get two categories that are high numbers and two categories that are low numbers. The two categories that are high numbers are your parentals. The two categories that are low are your recombinants. And the number that we need to figure out is the percent recombinants. So let's do that. So you could do this, once you get going, you could do all of this in like half an hour probably. Doesn't seem to like this. All right. So let's take this and we'll put it somewhere where we can write on it. So let's say PowerPoint. So what do we do with this information? We say All right, so you don't even have to know anything about, as long as you know that this was a good mapping cross, meaning heterozygous for 2 genes, cross to homozygous recessive for those 2 genes, that's a legitimate 2-point mapping cross. So what we did is, let's see, I think I have to do this. Yeah, PowerPoint's not the greatest. So what we ended up doing was crossing. So our cross was, we made it something that was heterozygous for shaven and eyeless. And we'll make that heterozygous. So it was heterozygous for these 2 genes. So that was the second cross. So a mapping cross is always something that's heterozygous for 2 genes. And then we're going to cross it to something that's homozygous for those 2 genes. Now, because of autocorrect, so ignore the capitals here. All of these things are recessive. Probably as a seasoned geneticist, you might not have picked up on that. But if I see that, I just automatically think of that as dominant. Okay, so that's the cross. And so what can we get out of that cross? So we can get this chromosome. So our original parents were shaven and eyeless crossed to wild type. And so now in this female over here, that's the way those genes started out. So that means that what we're going to see is shaven and eyeless is one parental, because that sort of started out together. Just wild type for both genes is our other parental. So this, we know this part because we set up the cross and we know what we started in the parent generation. So the parent generation was shaven and eyeless crossed to wild type. So those were our parents. And then our recombinants are going to be just shaven, but wild type for eyeless, or wild type for shaven and mutant for eyeless. So that's what we expect to be our parentals. So this should be a parental. This should be a parental. This should be a recombinant. This should be a recombinant. So that's our results. Let's move this up a little bit. Here's our results. Well, I guess we'll leave that there. But we don't even need to know all that. If we look at this cross, or these results, the 2 that are the highest are the parentals. So if I didn't even tell you what the cross was, and I just said some random cross was done, and all I know is that it was a 2 heterozygotes, or a dihybrid test crossed, and I got these results, you could look at this and say, well, these top number and bottom number are the highest numbers. So they're the parentals. And the other two are the lowest numbers, so they're recombinants. So you add up the recombinants. So to calculate map distance, it's the number of recombinants over the total. So always make sure you put it over the total. Sometimes people will put the number of recombinants over the parentals, and that doesn't make sense because we want it to be a percent. So what percentage of these offspring are recombinants? Well, the numbers are, we got 10, and they even give you the total here. Well, that's a big number. No, 10, no, that's right. 10 divided by 1011, and that's going to be about 1%. And if you, the other thing they do for you in this program is they give you the proportion. So you could just kind of add these proportions up. So 0.004 plus 0.006 is 0.010, which is going to be the same as what this is. Or you can just divide this. So you want to divide that, and multiply it by 100% or $100. No, 100%. Get out your handy dandy phone. And now we got, it's going to be 1%. So 10 divided by 1011 is 0.00989. So that's 1%. So that's pretty close together as far as genes go in genetic mapping. And so the way we would represent that is we would say that our genetic map for these two genes are SV and ILIS have, so that's our map, SV and ILIS 1.0. So that's how you do it. And you do that same thing for every combination of your genes. So when you have 6 genes, that's going to be something like 15 combinations. So you're going to have to do A cross to B, A cross to C, A cross to D, etc., etc. But it won't take very long. Okay, so now let's do let's see, where were we? Let's get rid of this. Sure, let's save it. All right, so now we're back here. So we're done. So we did those. Now the other thing that you might come up with, there's only 2 genes that are X-linked or that are on the 4th chromosome, so we won't do that. Meaning I won't do a 3rd one. But let's do an X-linked one. All right, let me pick a couple of so X-linked is pretty much the same. It's pretty much the same cross. But it's just one simple thing that's a little bit easier. So I'm going to take 2 genes that I know are X-linked. So let's say forked is X-linked and white is X-linked. So we don't want to do it this way. So let's remove that flag. So we want to make the female wild type again. So always make the female wild type. Makes life easier. And your male has to be mutant. Yeah, definitely do this one. If it's X-linked, do it this way. Meaning make your female wild type. And the male we have to design. So we're going to do, what did I say? I think I did a bristle, an eye color. So now my male, you can tell it's a male because it has this little black segment at the bottom. See how this is kind of striped all the way down and this has a little black segment at the bottom? That's how we determine males. Males also have these little extra bristle things up here called sex combs. So that's how we know they're male. And we also know it's male because right here it says male. All right, so we're going to make these flies. What do we got? So these are the offspring, both wild type for everything. So if you think about X linkage, that makes sense. If we start out with X-linked female, cross the mutant male, then we end up with all wild type. Oh, so we can do that. So we're doing it the same way. So we can select this female, and we can select them there. Now she's homozygous or heterozygous for both. He's mutant for both. He's not technically homozygous for both because he doesn't have 2 X chromosomes. He's got an X and a Y, so we call that hemizygous. But anyways, it's the same thing. So if you make those, we get and analyze it, ignore the sex, we get some numbers. And we get 345 and 350, those are the parentals. We get 163 and 173, those are the recombinants. We can even just add these numbers up. 15.8 plus 16.7 in terms of percent. That's like 32, 33%, something like that. So we can calculate that out. So they're linked because this is not 1 to 1 to 1 to 1. It's something different. If we did a chi-square, it would definitely show us that that's something different. And the way we calculate this is we add 163 plus 173 divided by the total. 163 plus 173 is 336 divided by 1031 is 32.3. So this is 32.3%. That's the map distance between those two. So there you have it. Now I kind of did that. There's another way you could do this. And so let's do that. Let's do a new cross. Because it's X-linked, there's like a shortcut. We can actually make the female mutant for both genes. And we can cross her to wild type. And we made them. And now, because this is X-linked, the females are all wild type and the males are all mutant. So we did this for one gene. If you just thought about the white gene, if you start out with a fly that's homozygous for the X-linked white gene, cross that to a male, what we saw before is all the males are white. Now we just have two genes on there. So we have forked and white, all wild type. The males are forked and wild type. So these males are forked and wild type over a Y chromosome. And these females got the forked and white from mom here and the plus plus from dad. So she's heterozygous for both genes. He's hemizygous for the mutants, which is, for all intents and purposes, is homozygous recessive, same difference. So let's just make these. So now we can just mate our F1s. Now in this program, it doesn't make much difference. We could have easily just crossed that female back to the male or whatever we want to do. But in real life, if you're doing a cross and you do one cross and you let those parents mate and lay eggs and then you clear out the parents, and then when the next generation comes out, you just let them mate with each other and have babies, that's a lot easier than having to pick out specific females and go find a specific male. So it's just kind of a technical thing. But now, so we just did the same thing. We'll analyze it, ignore the sex. Yeah, we got 17 plus 16, which is like 33%. Now, these are never going to come out to be exactly the same because this is programmed so that it looks somewhat random and looks like real data. And so there you have it. So that's how you do X-linked ones. Pretty much the same. Actually, you can pretty much do the same thing for X in autosomal. All right, so now I want to show you one more thing. And the easiest way to show you that, I think, is to open up this program I've been playing around with called Smooth Draw. And I just want to show you how to map. So once you've mapped some genes, how do you make a map of like more than two genes? So in order to map any I'm having getting my pen to show up here. All right, so let's say we do that. We have two genes, A and B, and we do a mapping cross, and it comes out that these are 5 map units apart. So that's 5% recombinance in that type of cross that we just did. So that gives us a map between A and B. And then we do A and C, and we get 10 map units. So now what we know is that A and B are 5 map units apart. And we know that C is 10 map units away from A. So C could be over here. But it could also be to the right. So we have A and B, and that's 5. And we know A and C is 10. So A and C is 10. If that were the case, then this would be 5. If this were the case, so I'm saying this, in this case, we knew that A and B were 5. And then we showed that A and C were 10. And it's possible that B is right here making B and C 5. That would add up to 10. But C, because all we know about C is that it's 10 away, but we don't know if it's 10 to the right or 10 to the left, so it could be 10 to the left. If A and C, if C is to the left, then C and B is going to be 15. So we have to do another cross and map the distance between B and C and see what we get. And let's say we get... well, let's just say B and C, let's say we get 15. So we just have to map this out. We get B and C is 15. It makes more sense with this left model. So we don't, so the left model, the left map is correct. So what you're going to do is you're going to calculate these distances, and then you have to put them into a map. So how do I put these into a map? The super easiest way is to take the one that's farthest apart and say, I know those guys are on the outside. So that makes it super easy because you already have these, you're going to have all the data. So you take B and C, you say they're 15 apart, and I know an A must be in between there somewhere, and it's closer to B than it is C. So we put it over here. And A and B is 5, and A and C is 10. So you get a map like that. Then the one last thing I'll say is sometimes, so let's put this 5 up here. So the 5 is the distance between B and A, and the 10 is the distance between A and C. What you'll most likely see is something like this, where that's 13, and this is 13. And that's frustrating, particularly first time around, because you're used to things adding up, right? You're used to science, things should be precise. But because this is dealing with biological organisms and things aren't always super precise, it's not like a, I don't know. But there's also stuff going on inside the fly with crossing over that makes it so this is inaccurate for like good reason. So that's okay. So a lot of times they won't add up exactly, and you just have to come up with your most, your best map that you can come up with. But what will always be true is the ones that are the farthest apart, the biggest distance, you put them on the ends, and then you just kind of put your A, or whichever one's in the middle, you put in the middle, and you put it somewhere relatively close to that. All right, so I'm not sure how long this has been, but it's probably long enough. Hopefully that's enough you can get started on this project, and of course, always let me know if you need any help.